All right, so let's just take a few moments to get focused again. I'm going to talk you through like a 2-minute little mindful breathing thing. If meditation, mindful breathing is not your jam, that's totally fine. Just sit quietly. Otherwise, see if this might help you focus. So make a start by putting down any pens, pencils, things like that, making sure that your feet are comfortably on the ground. If your phone is looking at you, maybe just turn it over. And make sure that you're sitting up comfortably enough to get a little extra oxygen, but not super uncomfortably. If you feel comfortable, close your eyes. Otherwise, just look somewhere peaceful. I'm going to start by listening to the sounds around. So see if you can identify the furthest away possible sound. And gradually start bringing your attention closer and closer to you. And now slowly transfer your attention to your breath and just start noticing how your body changes as it breathes. So follow the breath as it comes in through your nostrils. Notice the temperature. Notice how your chest and your belly expand. And as you breathe out, notice that your shoulders automatically relax, your belly relaxes. And for 3 whole breaths, see if you can just notice your body changing as you breathe. That's all you have to do, just breathe. So we're just doing some mindful breathing. So just take your attention back to your breath. 2 more breaths, just breathe. Notice how you're breathing. Two more breaths. See if you can just focus on your breathing, even though you can hear other things happening. One more breath. And start listening to the sounds around. Wiggle your toes. Give a stretch. Give a yawn if you need to. And if necessary, open your eyes. All right. So, that was what we're talking about as far as derivatives go. And now we are trundling swiftly into chapter 14, which is integration. So just to swap the ideas of integration back, here's what you did in calculus. So the idea in calculus was you have some function of one variable, you want to find the area under the curve between 2 points, roughly speaking. How did you do that? Well, you chopped up your domain into a whole bunch of things, and then you looked at the little rectangles because we know how to calculate areas of rectangles, and then you let your delta x's get smaller and smaller and smaller, and hopefully with some magic, as you let delta x go to 0, and also the number of rectangles go to infinity, and your function was well behaved, then you got some number by adding up all those little areas, and that number is what we call the definite integral. And you might have talked about upper and lower Riemann sums. So do you take the area underneath the curve, or like where there was a whole bunch of stuff that you did, it was annoying, and then you did like something between the lowest sum and the upper sum, and you got this number here, and yay, and it was all great. And you ended up with this bunny over here, which says that this thing is defined as the area of this curve, under this curve between A and B. Yes, okay. And yeah, okay. So what is it that we're trying to do here? We are essentially trying to do the 3-dimensional analog of that, which is I have some surface and over some particular little domain, I want to find the volume underneath that curve where this is my kind of my bottom. Yeah? So I'm looking for volumes. So at the moment we're just thinking about integrating functions of two variables, so surfaces, and we're finding the volume underneath them. And we will define the double integral to be this thing over here, and we'll figure out how to calculate it in a moment. How do we do it? Well, we break things up into small bits like we always do with calculus, except now we break it up into little squares. So a little delta x times a little delta y, that gives us a little square, and we can work out, and we use cuboids. Cuboids? Yes. And we get an approximate area for this, and we add it to all the other approximate areas, and we do the same thing. We let our little delta x and delta y go to 0 and have an infinity of them, and then we get this hairy looking Riemann sum over here, which when we take the limit, phew, okay, great, gives us this thing over here. It's a double integral, so it says you need to integrate with respect to x and y. That's why we've got two things over here. And you can talk about all of this crazy stuff with epsilons, but we don't need it for this course. Okay, so that was a whirlwind tour of the theory behind double integrals. We are doing exactly what we did with functions of one variable, except in 2 dimensions by chopping things up and adding up volumes instead of adding up areas. But actually, what we end up doing is mainly actually still thinking about single integrals, as you'll see in a moment. So let's think about how we practically could work out this volume. So we're going to take a couple of simple cases and talk through it. So I've got my surface over here, which is this thing, this S. But what I'd like to know is what is the volume of this weird kind of TARDIS-shaped thing, where on the xy plane, I've got this floor plan, and I want the area above it, but below my curve. How could I work that out? So to make this a little bit easier to see, I'm actually just going to delete this surface, because otherwise I'm just going to have too many lines. So I'm just thinking about this. Well, breaking it up into the little blocks is kind of frustrating, and it's not clear where you would go from there. But one thing that you could do is you could slice this like a loaf of bread, and you could work out the area of each of those little slices, and then multiply it by a little width, and that would give you the area, the volume of that slice, and then you could do that for a whole bunch of slices. And that is, in essence, how we, in practice, do integration of double integrals like this. So the case that we're looking at over here is a bit of a special case, so I don't have wavy lines all over the place. I'm saying that the domain that I'm looking at is bounded by the lines x equals a and x equals b. So you'll notice that I am straight in the y direction. So if I plot this, I'm plotting x and y down here, my base looks like this. So my y changes according to dx and cx, but my x has a shape like that. Yeah? And what I'm going to do is I'm going to look at, let me pick a nice color. Okay. What happens if I slice, so I'm thinking about slicing like that. So I'm thinking about this slice over here. Okay. Well, here is my here is a cross section of the slice that I just took, and it will look something like this. If we go back to, so I've sliced it somewhere like here. Well, I could work out the surface area of that slice quite easily based on this up here. It goes from whatever my x value is, will give me my y value of c of x, and it goes to d of x there. The sides go straight up, and my function is just changing however it is for those x and y values. So if I want to work out the area of that slice, I can just do straight normal integration. I'm integrating from c of x to d of x, this thing, with respect to dy. So this thing might have x's and y's, but because we're integrating with respect to dy, we don't care about the x's. X is not changing. I've made a slice in the direction where x is not changing. So I'm doing the same kind of thing that I did when I was taking derivatives, was like, I don't know how to do this in general, let me hold something fixed. So in this case, I'm holding my x fixed, and I'm just looking at what's happening in the chain in the y direction, and I'm just integrating in the y direction. Okay, so I could do this integral, and that would give me the area of that, which would depend on where I was in my x. So I would end up with a function of x. Yes? But then, finally, we want our double integral. But in fact, that's just going to be, so but we've just worked out that at least part of this is just a of x. So then I'm just going to integrate this a of x thing that I found from a to b, and I'll be done. I realize that this is possibly not super helpful. We will do a bunch of examples, which will make it much clearer.
I don't know if I missed the beginning, but I don't get why we're doing this. Like, what is the goal?
Well, the short-term goal is to pass the exam.
Sad.
Okay, but the longer-term goal is often we want to integrate functions of two variables. It's all the similar things. Why did you learn integration of one variable?
You're asking me.
Yes.
Oh. I guess you have to be able to calculate like the area or something on their
Right.
function.
So anytime you want. So this is calculating volumes.
Okay.
But it also might be in the same way that with calculus of one variable. What happens if someone tells you the rate of change, but you want to know the actual thing? You have to integrate.
Okay.
So here you might be told the rate of change of your surface, but you don't. You need the actual surface.
I see.
Yeah. So any of the reasons for integrating in one variable apply here.
Okay.
Yeah. Okay. I think I will come back to this in a moment. Let's rather look at an example. Okay. So what we would like to do is we want to find the volume of that purple thingy over the particular triangle T which I've shown there. So I need, what we want to find is the volume of this prism thing here. I seem to have lost, okay. So the thing you need to know is that this purple thing here is, let's rather do this. Okay, so the surface that I'm looking at is the surface z is equal to x times y, and it turns out that it looks kind of like this if I'm just looking at it over the particular base that you have here, xy, which is this triangle. Okay. So for the moment, don't worry what y simple means. We'll come back to that. Let's think about how we would work this out. Well, we've seen that chopping in one of the directions is helpful. So what we're going to do is we're going to chop our domain in the x direction. Turns out we can do it in both. And then work out the area for each little bit. So remember, we've got our function coming up like this. So we're chopping here, and we're saying, okay, what's the area of that bit? And then we add it to the area of that bit, and chop, and chop, and chop, and off we go. That kind of makes sense? Okay, So we split it up. So let's think through how we're going to do this. Well, we're chopping it up. I just want to check which way around I wanted to do this. Okay, I don't have those notes. Okay. We're going to chop it up in the same way that we did for this example here. So we're holding x constant and we're chopping parallel to the y-axis. Okay, so we're making our chops like this. Chop, 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 chop. And if we think about what that looks like here, we're chopping along like that. I think, did I get that? No, that's not the right way. Oh, yes, no, that is correct. Okay, I think we're right. Okay, so we're going to, so our dA, our little area, is really made up of a dx by dy. So what you're thinking about with your areas is that you're breaking this up into little bits here, which are a dx times a dy. Those are kind of the floor plans. Bear with me through one of these examples and you'll see where it goes. So what I'm going to start by doing is I'm integrating according to dy. So I need to know where my y starts and where my y ends. Sorry, I'm just feeling like I've left out an example here. Let me just go back. Oop, okay. Okay, so what I need to know, since I'm going to be integrating each of these with respect to y, I need to know my limits for where my y starts. So my y always starts when y is equal to 0. But what is the height that it reaches? So what is this value over here? Well, I need some function that's going to tell me, because how high it goes depends on where we are in x. This line is the line y is equal to x. So I will always be integrating. If I wanted to know just the height of that line, I would integrate from 0 to x, or y is equal to x. So I would have I'm not doing a great job of this, and I'm trying to think of a better way to explain it. Best way to explain this. Okay. So I want to essentially find the volume, the area of a slice that I've taken like that. Yes? What do I need to know in order to find the area of that slice? I need to know, so it's going to look something like that-ish. Well, I need to know where it starts and ends, and I also need to know the height. The height will give me my xy. Where does it start and end? Well, for the way I've drawn it over here, it starts on that line there, which is the line y is equal to x, and it ends over here at 1. So I think actually this drawing over here is incorrect. I will need to... so that is correct. So this is correct, so maybe this is wrong. But that, no, that also looks right.
It's the two different directions. So starting from x and starting from y.
When you write on the left, you see it from the y.
Okay.
But it's
Which one is incorrect? So this is the right.
They're both
right
correct.
one.
They give you the same answer. It's just that like, it's whether you're looking at it from set x or set y.
Your right graph has a problem because you have a dot on the, you have a vertex at 0, 1. You have a problem with the xy axis. Like you shouldn't have a point at 0, 1, but at 1, 0.
Okay. Thank you.
Yeah.
All right. So I should have actually drawn that triangle,
Yeah.
not this triangle. Okay.
Yeah.
So that's what's going on. All right. Sorry about that. But the same reasoning holds. We are chopping like that. Okay. Maybe we should just call it. Yeah. Okay. So I will come back to this example. What we will do for the last moment is to talk about how we go about tackling double integrals, which might be more helpful in this. So you've got this thing which basically says break the area of your domain up into a whole lot of dAs and integrate this thing miraculously, and it's not clear what to do. But we can split this into integrals with respect to x and y, which we know how to solve. And the way we do that is we look at the domain over which we're integrating. If it looks like this, so our x, we always integrate from the same x value to the same x value. So we've got these straight lines here, but our y changes. The way that we split it up is we will integrate first with respect to y. So I should put over here that this is c of x, sorry, that's... Wow, this is terrible notation and I apologize. Okay, so that is a function d, which tells you how your y changes with respect to x, and this tells you how your lower limit of y changes with respect to c. So if that's what your domain looks like, first you'll do this integral like so, and then you will get out of this a function of x, which you can just integrate normally. If, on the other hand, you have the opposite situation, like so, then you'll integrate by x first, and then with respect to y. I think, and I will put the solution to this into the notes so that you can see an example of what I'm talking about, because this is one which you can do in either way. So I will correct that photo and put the two examples in. All right. And I am going to put some integration into the tutorial on Thursday, because actually just getting your hands dirty is the best way to go about it. So there will be some in the midterm. Okay. All right. Good job, everybody.